This lecture will be a brief introduction to neural networks, in particular the multilayer perceptron. Neural networks are a very large field of machine learning and are growing. This field is growing very rapidly in recent years. So we don't have time in this course to cover a significant part of this field. However, there will be a course on the next semester dedicated to deep learning, so specifically about neural networks. In this lecture, I'm only going to give a brief idea of the basic notions behind artificial neural networks. So I'm going to talk about the perceptron, the problem of linear discrimination with a perceptron in the original sense. Then what we now call the multi-layer perceptron, which is basically a network of neurons which is capable of nonlinear discrimination. We are going to see a bit about backpropagation and how to train these networks and how to do regularization in multilayer perceptron. But this will be just a brief introduction to give you some general idea, and we are not going to go too deeply into this subject on this particular course. So the idea of the perceptron is inspired on the biological neuron. And this is a cell that is at the core of our nervous system, our brain, and it has these dendrites, these branches here that we can think of as receiving the input. They are sensitive to stimuli. And then they have these synapses here at the end of the axon, where we can think of being the output. So when the neuron is activated, there is an output here, a release of neurotransmitters that can then stimulate other cells, for example, a muscle cell to contract, or other neurons to propagate the signal in a network. So the way this neuron works is with a nonlinear response. If the stimulus is too weak, then the depolarization in the membrane here is not enough to pass on to the axon, so there is no response on the output of the neuron, so to speak. But if the stimulus passes a threshold, then the membrane depolarizes and quickly this depolarization wave on the membrane propagates through the whole cell, through the axon, and then it will stimulate the release of neurotransmitters here at the synaptic terminals. So this basically means that the neuron either fires or it doesn't fire, and it has some threshold depending on the combination of stimulus it is receiving. We can model this mathematically by coupling a linear combination of the inputs. Let's say we have this vector with n terms here, n elements for the features, the x input vector. We have one weight for each of the features, and this will be summed, the product of the feature and the corresponding weight will be summed into this term here. So basically we can think of these weights as representing the sensitivity of the different dendrites to the different stimulus, and when we combine everything, we have a linear combination of all the inputs here. And now to model this all or nothing response of the neuron, we pass this through an activation function that is nonlinear. For example, it's just a threshold and it either answers 0 or 1 on the output. So this was the idea of the original perceptron, which worked like this. We have a linear combination of the inputs with some weights that are parameters of the model that we can adjust. We have an additional free weight here that we can use to adjust. So this is the equivalent of adjusting the level of the threshold. And now if this whole thing, this y here, is negative, the output is 0. We do not fire the neuron. If it's positive, then the output is 1. So basically, by adjusting these parameters, we can specify the sensitivity to different inputs and to the overall input and decide when the neuron fires. And now to train the perceptron, this model here, it was just the training rule consisted of finding the examples where the output we get from the perceptron is different from the target output. So if we have a binary classification problem, we have examples in class 1 and class 0. We take the difference between the output of our perceptron and that target class. If this difference is 0, then there is no adjustment to be made to the weights. But whenever the difference is not 0, then we multiply it by a small learning rate constant so that we don't take too large steps. And then the product of that with the corresponding weight, with the corresponding input, will tell us how much we need to change the weight. So we adapt each weight whenever we find an incorrect example in proportion to the input value that is passing through that parameter and the difference between the target value and the output of our perceptron. So this was a way of training the original perceptron. The perceptron was this model here that is actually modeling a neuron, because we have something that has this linear combination of the inputs and then a non-linear response that is all or nothing, depending on whether it passes the threshold or not. Now, one problem with this is that this is just a linear model. So basically the perceptron could be trained, and there was a lot of hype at the time, but it's just a linear model, so it's very limited in what it can do. And it's not possible to train by stacking these perceptrons, because then we cannot figure out what the learning rule would be. But we can adapt this function here in order to have a differentiable nonlinear activation function, and then this allows us to train networks of these perceptrons, or of neurons in general. So instead of using this stepwise function, this function that after some threshold it outputs 1, below that threshold it outputs 0, we can approximate this with a function that is continuously differentiable, for example the sigmoid function, so that we can compute the derivative at any point. So this is close to this one, but does not have those sharp edges there that can give us problems with the derivative. Now, the perceptron originally is this single neuron model by Frank Rosenblatt in 1957 with threshold activation and so on. Currently, it's generally used for neurons, and the multilayer perceptron is basically a fully connected neural network. But in any case, we will not worry too much about these names. The important is the basic idea. Okay, so let's look at one neuron and what we can do with a single neuron. Since one neuron has this linear combination of inputs followed by a nonlinear activation, we can classify linearly separable sets. For example, consider this would be the OR function, true, 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 and false here, if we consider 0 to be false and 1 to be true. And we can minimize, for example, the quadratic error between the output and the class, and adjust the parameters. Note that this, since we have this nonlinear sigmoid activation, we are not really having this problem of pulling the discriminant far away from the place where it should separate the two classes. And we basically present each example, and we compute the error, which would be the difference between the class that is being predicted, output by our neuron. Our neuron is going to output this sigmoid function, so it should be close to 1 for class 1 and close to 0 for class 0. It's a bit like trying to predict the probabilities as we did in logistic regression. And in fact, we can interpret this sigmoid function as a probability. It varies between 0 and 1. So we consider this error between the predicted probability and the class, and now we minimize this by sliding down the derivative of this error. So basically we can compose the derivative to find the derivative of the error function with respect to each particular parameter, to each weight, we can, and so that we slide down in that direction, so this is why we have the negative sign here, we can use the derivative of the error with respect to that sum that we are obtaining when adding all the inputs into the neuron multiplied by the weights. Then we have, this is that one here. So we have the error, the derivative of the error with respect to the output of the neuron, then the derivative of the output of the neuron with respect to the overall sum of the inputs multiplied by the weights, and this output will be the sigmoid function here. And then we have the derivative of this sum with respect to each particular weight. So if we want to compute how much each parameter in our model is affecting the error, we need to compose all these derivatives. So looking back here at the model, what we're doing is that we have an output here, we are measuring the error to some target value, and now we are computing the derivative over this sigmoid function, then over this net weighted sum of all the inputs, and then with respect to each particular weight according to the input that is passing through that. Okay, so chaining all these derivatives, we get this formula here. This would be the derivative of the error. This is a quadratic error, so the derivative would be like this. If we take 1/2 of the quadratic error, it will, when combined with that 2 that comes from the square, it will disappear into a 1. So we have this derivative here, and then we have the sigmoid function s. The derivative is this one with respect to the input into the sigmoid function, and then we have the derivative of this weighted sum with respect to each particular weight, that in this case it will just be the value of the input there. So if we multiply all these derivatives, we get the derivative of the error with respect to each individual weight, and this gives us the update rule. So we're going to change the weight slightly using a small constant, this training constant here. If we have only one neuron, we can use something like this. If we have a large network, it's often much slower, and the update is actually more sophisticated. But the idea is that we take a small step in the direction where we are sliding down the derivative, and we compute the derivative by chaining all of these derivatives, and we have the update rule here. So, of course, this depends on the activation function. This would be the update rule using a sigmoid activation function. If we have different activation functions, the formula would be different, but the idea is always the same. Chaining these derivatives so that we know how we need to change the weights in order to reduce the error. Okay, so the intuitive explanation here is that we have a target value. We have an error between the output and the target value, and we consider this error squared in our error function. And now we have all these derivatives, the sigmoid, the weighted sum of the inputs multiplied by the weights, and all the way down here, so that we find the derivative of this error, the difference between the output and the target value, with respect to this weight here, in order to update the weight so that we slide down this derivative and reduce the error at each step. And now we do stochastic gradient descent, where we can, for example, present one example at a time to the network. We compute the direction where we are sliding down the error surface. We step in that direction, we present another example, we step down, and we keep changing the parameters in our neuron in order to reduce the error that we find. This is called gradient descent because we are looking at the derivatives, at the gradient of the error, and trying to go down that gradient, so going in the direction where the derivative is negative. And it is stochastic because we are presenting the examples in a random order. This helps try to step out of a local minimum or avoid getting stuck here when trying to descend this error function. And so this stochastic nature of how we train the neuron helps with that. We can do this with online training, one example at a time. It's often more efficient to do batch training, where we use a batch of examples, we add the contributions to the update of all the weights for all these examples, and then we change the parameters in one go in a larger step. This usually is more efficient because we don't have to keep updating the weights of the neuron at each example. We can use a set of examples. And especially if you have large networks and you have parallelized computation with GPUs or something like that, this becomes a lot faster. Now let's see what we can do with one neuron. This is a series of runs. I'm presenting these 4 examples at random. Each time I present the 4 examples, it's one epoch. So one epoch is one pass through all the training examples over the network, which come in a random order, and then we can do a second epoch, third epoch, and so on. Since these are few examples, we need a lot of epochs to train, and you can see that the trajectories are slightly different, but mostly the neuron learns after maybe 1,000, 1,500 epochs. The error is already very low, and this is the separation we get between the two classes. So one neuron works fine for this kind of problem because it's a linear classifier. If we try to classify, for example, the exclusive OR function, which we can represent like this, it's true if one of them is true and the other is false, and it's false if both are false or if both are true. So now this set we cannot separate linearly, and if we try to train the network, we always get this. So this is 0.25 quadratic error. 0.25 is the square of 0.5, so it means that it's always getting 50% wrong. It's 0.5 away on average from the actual result, because it cannot do better than this. It is unable to adequately separate these two sets. But what we can do to solve this is to stack layers of neurons. So this is called the multi-layer perceptron. It's one of the names for a fully connected neural network, where we have different layers. So in this case, we have one output layer with one neuron, and then we have a hidden layer with 2 neurons, and both of these neurons contribute inputs to the output layer. The actual features are presented to this first layer, which is hidden. We don't see the output of this layer in the output of the network, and only after some transformation in this layer do they pass to the output layer. Now, one way of dealing with this bias here that helps us simplify. So remember that we have this sum of the weights multiplied by the input, and then an additional parameter that we can use to adjust the position of the threshold. This is true also if we are using the sigmoid, but one way of incorporating this into a representation and to simplify the expressions is to assume that we have here this bias neuron, this bias weight here that is just being multiplied by 1 and then added here. So this is the same kind of simplification we did with for example, the logistic regression classifier, where we just assume that we have a vector of parameters and a vector in the input, and we just add a 1 to the input so that we can have this independent parameter that serves as a bias. So we also need this bias value here, but in any case we can just represent everything in this way. So let's assume that all these activations are sigmoid. We have 2 neurons in the hidden layer, 1 neuron in the output layer, and now to train this network, we have now a set of neurons. We're going to have to compute the updates for all the weights in the output neuron and all the weights in the hidden layer. So for the output neuron, we can do the same as we did in the single neuron. but the only difference is that the inputs we are getting on the output neuron are not the actual inputs in our data, but are the outputs of the previous layer. But other than that, the expression is the same. We have the derivative of the error with respect to the output of the activation function, the derivative of the activation function with respect to that weighted sum of the inputs, and then we do that, we compute the derivative with respect to each of the parameters in this output neuron. The only difference now is that the inputs we have here are not the values of x like we had over here, where we multiplied by the features of the examples, but in this case, in the output neuron of a network, what we have to multiply here are the outputs of the previous neurons. So this is this delta that we have that we're going to multiply but by the inputs into this neuron, but the inputs into this neuron are the outputs of the previous layer. And now for the hidden layers, what we need to do is we keep propagating. So we have the derivatives that we computed on the output layer. If we have several output neurons and this particular neuron in the hidden layer is contributing to several output neurons, we have to sum all of those contributions of the several output neurons. But this is the derivative of the error with respect to the activation of the output neuron, then the activation with that weighted sum, and so on. And then we keep chaining back until we get to the weights of the hidden neuron. And we keep going backwards. If we have more layers, we keep doing this backwards in order to propagate the error. So intuitively, what we're doing here is, suppose that we have a network like this. There are two output neurons that have some target values. We need to compute for each of these output neurons. We need to chain the derivative of the error, here given the error function, the activation, the weighted sum of all the contributions going into that neuron, and the passing through this particular weight that connects to this neuron here, and then continue over the activation of this neuron and all the way to this particular weight that we want to update here in the hidden neuron. If there are more than one neurons in the output layer, we need to add the contribution for these different pathways in which the error is propagating backwards. And if we have more layers, then this just gets more complicated, but basically we are just multiplying all of these basic derivatives for each particular step. So you can see that this is easy to automate with the backpropagation algorithm does this. It just automates the propagation of the error through the whole layer. So the idea here of the backpropagation algorithm is to first present an example to the network, propagate the input forwards through all the layers. So if we present here the network with some example with values x1 and x2, we activate these two hidden neurons, we use the output of these to activate the other neuron, and if this is a large network, we can keep doing this all the way to the end of the network. So once we do that, we're now going to compute for each neuron this delta, which is the contribution of all the derivatives that come between the output of that neuron and the error at the end of the network. So for the output neurons, we just need to compute the derivative of the error function and the activation function and so on. But then for all the hidden layers, we will have to continue this backpropagation, so continue multiplying all of these derivatives. And so we are going to take the contribution of all neurons in the front layer, and then the activation function and the weighted sum for each particular layer as we go back in the network. So then once we have all the deltas for all the neurons, we can update the weights for all the neurons by using the delta for that neuron multiplied by whatever value is input into that particular neuron. Note that for the neurons in the first layer, this is actually the input, the features of the examples, but for neurons in further layers deeper inside the network, these inputs will be the outputs of the previous layer. So basically, we can automate the computation of the updates for all the parameters in the network as long as we can chain all the derivatives. So if all our activation functions are such that we can compute the derivative, we can backpropagate this and train the network no matter how large it is. Of course, if you have a very large network, then multiplying all these derivatives can get you to very small values, and the training may eventually stop, and this leads us to problems with deep learning that will be covered in another course, but this gives you the general idea how to train a neural network. So let's see what happens here when we do this to solve the exclusive OR problem with this small network. We can see that in different trajectories it may take more or less time for the network to learn, but most of the times, even with this number of epochs, 20,000 epochs, we can get it to learn, and we get this result at the end. So we can separate the blue class from the red class in this way. But what is happening here, the reason why we can separate, is because the hidden layer is creating a transformation of the data. So this is the training of the network as we progress here along the training from the perspective of the output neuron. And the output neuron is not seeing the actual coordinates of the points, but it's seeing what the hidden layer is presenting to it. So one of the neurons in the hidden layer, this one here that we are representing in the horizontal, is separating this point to one side and these 3 points to the other side. So basically it's doing something like this, like what we have here, only it has one blue point in this side and one blue point on that side, but this is a mix of red and blue, because this is what one neuron can do. One neuron cannot do better than this. So this is what we have here for this neuron represented here in the horizontal axis. It's going to leave out this point on one side and the other 3 on the other side. But this neuron on the vertical axis is doing different. It's leaving out this particular point and the other 3 here below. So when the output neuron looks at this representation of the data, it can easily find a straight line to separate these classes. It separates the red here and the blue there. So this is what is happening here in this classifier. When we finish training, we have this separation between the blue and red classes because of the nonlinear transformation the hidden layer has done. So this is basically the secret or the great power of artificial neural networks, is that those kinds of transformations that we need to do in order to apply a linear classifier to a problem that cannot be solved with a linear classifier. So first we transform the data. In the case of a neural network, these transformations are learned by the network itself. The network learns what is the best transformation to solve the problem. So if you have a large network, you can do very complex transformations of the data and do things like identifying images of cats or things like that that are very complicated to do. There are some different things we can do with neural networks. This is a classical example from Meacher, the auto-associator. Nowadays it's called an autoencoder, where we can take our data and create a network that outputs the same as the input. So we don't need class labels or things like that. We are just training the network in order to minimize the difference between the output and the input. And the output has the same dimension as the input. But what we do is we force the network to learn some good representation here by, for example, constraining the number of neurons we have. So this is the Mitchell's example. Suppose that we have 8 neurons as the input, 8 on the output, and we are using a binary representation where one of these is 1 and all the others are 0. So only one of the 8 can be 1 and the others are all 0. We have 8 different combinations here. Now we train this with backpropagation in order for the output to be the same as the input, but we are forcing the network to reduce this set of values into a representation that only has 3 neurons. And what we can find here is that when we train this autoencoder, we find, for example, this varies depending on each instance, but this is an example. For input pattern 1 followed by zeros, we get an activation here on the hidden layer of 101, for this one 010, 111, and so on. And here we have the 8 different combinations, as if we were writing 8 different numbers in binary. So we can train the network to learn this compact representation of this data set. So this is another possible application of neural networks. In this case, this is a multi-layer perceptron. We still have everything fully connected going forward, but if we constrain the layer where we have the representation, we can get something interesting being learned here from the data. So in practice, we usually start with these weights close to 0, because the sigmoidal function saturates rapidly away from 0. If we start here, we have a better response. And we start with random values, because if we don't randomize this, then all the neurons will be trained in step, always get the same updates, and will basically be just copies of the same neuron, and the network will not have the power it needs to transform the data. So we start with random values so that all neurons start differently, and then we train the network. Since initializing the network and the order of examples, all of this is random, we can expect that different runs of the same network with the same data do not be exactly the same. So there is some variation between different runs. It's useful to standardize the inputs, especially we should not get to values that are too large, or values that are at different scales in different features, because since we have the same learning rate for everything, and these activation functions can saturate, and also we can have numerical problems as usual. So remember, always standardize the data. And if we have, for example, a binary classification, we can use this sigmoid, this logistic function that outputs a continuous value between 0 and 1 as an estimate of the probability of belonging to class 1, for example, just like we did with logistic regression. If we have more than 2 classes, we can use multiple output neurons, and then there are some activation functions like softmax to interpret this as probability, or if we have multiple labels, that is, the same example can belong to several of these categories at the same time, we can use several sigmoid outputs and so on. The idea here is that the architecture is very flexible, and we can adjust it to different problems. When we are training, we usually use stochastic gradient descent. We have a random order for the examples. Generally, they are passed through in batches, and one epoch consists in passing all the examples of the training set, and then we restart another epoch by reordering at random and passing them again. We can evaluate the error. This now depends on the actual what we are trying to do. So typically for classification, we don't use the quadratic error. I showed this example here because it's simpler to show the derivatives and so on, but there are lots of different error functions depending on the application when we do that maximum likelihood approach that we saw before. But the idea is the same. We can do training and cross-validation, or training and validation. Typically with large neural networks, we also have large data sets, so generally cross-validation is not widely used. This is because large neural networks tend to take longer time to train, and if we have a very large data set, we don't gain much by doing cross-validation, validation is usually adequate. So you can do cross-validation in training neural networks, and if you have a small neural network, that's okay. But if you are doing, for example, deep learning with large neural networks, then usually we have a training set, a validation set, and a test set. That makes more sense in those conditions. One way, a practical way of doing regularization with neural networks is to do early stop. So this is an example of the training error here in red and the validation error in blue. And I'm doing, in this case, a 5-fold cross-validation so that I show different trajectories here. But we can see that in general, after around 40 epochs or something, we start having a larger validation error, even though the training error still reduces. So one way of doing regularization in neural networks is to find the best point to stop training, so that we avoid the network overfitting the training set, learning too many details about the training set. This is one easy way of doing regularization with neural networks. Other possibilities would be to penalize the weights. That is, we can decrease the weight values by a small fraction at each iteration. This is called weight decay. So basically, this is a form of regularization similar to what we saw in ridge regression, where we are penalizing large weights. And in this case, if the weights are not relevant for the error function, then they will tend towards zero, and we will tend to simplify the network in this sense. So this is another way of regularization in neural networks. But these are just some examples. But basically, the idea here is that we have this model of the neuron, and now if we use functions for which we can compute the derivative, we can chain all of the derivatives along the network of neurons and compute how we should update each parameter on each neuron based on the error function that we are considering. In this case, I gave an example, the quadratic error function, but this is just an example. There are many different functions that we can use. And also the network can be used for different applications with different architectures. So this is just a basic notion of neural networks. We are not going to go into detail on this type of classifiers in this course. So if you want, you can read chapter 4 of Mitchell's has a very good description of the backpropagation algorithm. This is this book is a classical for machine learning. It's very outdated currently, but for neural networks you have a very good description of these algorithms there. In Alpeiden's book, take note that the network described there has a linear output. So at the last neuron on the output layer, there is no activation function. And this makes the equations for the derivatives slightly different. But if you remember this detail, it should be easy to understand.